want to solve this system of equations in question 5. Now, I never start with the pen. Okay, we have the pen. So the first thing that I would notice is that we have 3 equations in 3 variables. So 3 equations. What's that? 3 equations and 3 unknowns, right? And so that means we can definitely find a solution, right? If there are more equations than unknowns, that means it's overdetermined, which means there might not be a solution. If there are more unknowns than equations, that means it's underdetermined, which means we're going to have kind of lines, planes, or hyperplanes of solutions. Okay. If we have 3 equations and 3 unknowns, that means we're going to have like one set of we're going to have a set of solutions. Okay, so also they should add the condition that x, y, and z are in the integers, because otherwise, then if they can take real values, then this has infinitely many solutions, and it's yeah, you're going to get some kind of I think it's going to turn out to be some kind of sphere of solutions. But if we work in z, then we don't have to worry about that, and we're going to get exact values which we can write down. Okay, the other thing I noticed is what's called cyclic symmetry. So these equations have cyclic symmetry, which means that basically the x, y, and z are interchangeable in the sense that if you have some solution, so let's say suppose we have a solution. This means solution. Like, just for example, x is 2, y is -1, and z is 4. Then we know that necessarily x equals 4, y equals 2, and z is -1 is also a solution, i.e. we can cyclically permute, we say, the x, y, and z. So in this case we've kind of moved x here, y here, and moved the 2 here, the -1 here, and the 4 to the front, right? And that's how we get this. If we do that, then we still have a solution. By the symmetry in that you can swap each of these around cyclically, right? I hope that's clear. If not, then let me know. But like, you can write it like this, x, y, z, if and only if z, x, y, right? By the symmetry. This is what we mean by cyclic symmetry. Okay, so that's another thing I noticed. Now with these problems, one strategy is always to substitute in, right? You could always substitute in x squared plus x minus 1 into this y squared plus this again, and then you've got like 2 equations in x and z, and then you can do the same here, and then you're going to have some horrific equation in x, right? It's always an approach. If you don't know how to do it, then that will work. But in particular, when there's lots of symmetry, as there is here, you want to exploit the symmetry. That's always your tactic. You want to try and find a repeating structure, okay, a repeating pattern. So I'm going to go over a couple of ways to do this. And the first way is this. So factorizing is always a good option. If you can see a factorization, then go for that. Or if you have a near factorization. So here, this left-hand side is nearly x times x plus 1, right? So I'll write this down. So we have x squared plus x minus 1 is y. And this is like x times x plus 1 minus 1, but we'll add the 1 to both sides, and we get this, okay? And so this, when applied to all the rest, is going to have a bunch of terms which are either x, y, and z, z is American, z is English, whatever, and x plus 1, y plus 1, z plus 1, okay? So I'll write those down. So we're also going to get by symmetry, again, I don't even need to refer if I just apply cyclic symmetry. And we see that these are going to be what the others reduce to. And now, when we multiply all of these together, we see that we're going to get x, y, z multiplied by each of these is equal to the same product of these factors, right? So in other words, how should I write this? X, Y, Z. I'll write this like this, and then hopefully you'll see what I've done. Wait, sorry, I'm about to mock up. Okay, let me just erase. Okay. So this is a 1. So if we multiply both sides, then we're going to get x, y, z multiplied by x plus 1, y plus 1, z plus 1 equals, I'll write it in a different order this time. I'll rearrange these so they're in the same order because it's the same. X plus 1, y plus 1, and z plus 1. And these are the same, okay? Now it's important here that we don't just cancel, okay? So what you might do is just like, oh, we can just cross these out because they're the same. And that's not true because one of them might be 0, okay? So if x is minus 1, for instance, you've just divided by 0 by doing that. This is a recurring problem which I'm sure will come up. So it's important to know that you can't just do that. The way to do it is to factorize, okay? So x plus 1, y plus 1, z plus 1 is common in both these terms, so we'll subtract and then factor it out, okay? So what that becomes is you have x plus 1, y plus 1, z plus 1, multiplied by, well, here we have x, y, z, and then we're going to minus 1 times all this. And we know this is equal to 0, okay? So now we know that one of these must be 0, okay? The only thing that you can multiply to get 0 is 0. So in particular, one of these brackets is 0. Now, x, y, and z are all integers. So x, y, z minus 1 equaling 0 means necessarily that the product x, y, z is 0. So we must have like x's, wait, this is, so we must have that either x is 1, y is 1, z is 1, x is minus 1, y is minus 1, and z is 1, okay, or cyclic permutations. Cyclic permutations. That means you could have like x is 1, y is minus 1, z is minus 1. Okay, here I think, okay, and then z is, and then y is 1, x is minus 1, z is minus 1. Okay, that just means you can permute these cyclically as we described above, right? So then what you could do is you could check that by throwing them back into the original equations, and it's going to reduce to something much simpler. And then you can find the corresponding values. So you can check whether these work, and then moreover you can see, well, if x is minus 1, then that will solve. So you can throw that back in and again solve them cyclically. So I'll do that here. So does x is 1, y is 1, z is 1 work? Well, 1 plus 1 minus 1 is 1. Yeah, that works. And then you know the rest are going to work by cyclic permutations. So this is going to work. What about this? X is minus 1, y is minus 1, z is 1. So we'll go back here. So minus 1 squared is 1. Minus 1 is 0. Minus 1 is minus 1. Y is minus 1, so that's fine. And here, minus 1 squared is 1. Minus 1 is 0. Minus 1 is minus 1, but z is 1. So this fails. So now if x is minus 1, now we'll say x is minus 1, and we'll say log. Now what this is without loss of generality. So again, we're invoking cyclic symmetry, and we're saying that, well, we'll look at the case where x is minus 1 and see what happens, and find the corresponding values for y and z. Generality. that's without loss of generality. So we'll say x is minus 1, consider the values of y and z, and then we know that any solutions we can get cyclic permutations again, right? We can swap the values of x, y, and z around cyclically. Okay, so if x is minus 1, then again going back to our original equations, which are here, x is minus 1 means z plus 1 is 0, right? I'll just add it here. So I'll go in green. So x is minus 1 means that z plus 1 is 0. And we know that from this y plus 1 is 0. Y plus 1 is 0. Sorry, I should have written these more neatly, but hopefully you can follow. And so by this, z plus 1 is 0. So we have y and z are both minus 1. So this implies z equals y equals minus 1, which is a solution we had before, if you remember. That's, oh no, sorry, we had the case 1, 1, 1. Okay, so we have a new solution now, which is x is minus 1, y is minus 1, z is minus 1. So I'll write that here. So x is y, is z is minus 1. And then cyclic permutations of this are going to be the same because every value is the same. Okay, and so now we know that we've got all the solutions because we've considered the case that this is 0, and then this is 0, but that's the same as any of these being 0 up to cyclic permutations. So we know that the possible values are, if we write it as a row vector like this, then this is 1, 1, 1, or minus 1, minus 1, minus 1. Okay, so those are the possible values. Now another way to do it, I'll cover briefly, and you'll be kicking yourself that you didn't see this because this is super easy. This is actually how I first did it, and then I thought about this. Is, well, again we're going to look at the symmetry, and we're going to think, well, let's try minusing the x from this side. So my first thought was actually, well, if you minus the x, then you can factorize this x squared minus 1 as x plus 1, x minus 1. So a really useful, I'll write in blue now. Let me just rub this out. So a really useful identity is called the difference of two squares. So if you have a squared minus b squared, this is a plus b, times a minus b. So for example, x squared minus 1 is x plus 1, x minus 1. This is an x. It's really poorly drawn x, but x. So okay, this is a really common identity. So that was what I was aiming for. So I thought, well, let's subtract x from both sides. So then we would get x squared minus 1. So x squared minus 1 is y minus x equals y minus x. And then similarly for the rest, so y squared minus 1 is z minus y. Z squared minus 1 is x minus z. And then we're just going to add this right hand side up and see that the y is going to cancel with the minus, add all of the right hand side. So this y is going to cancel with the minus y, the z with the minus z, and the x with the minus x. Okay. So then we're going to get the sum of the left hand side is, so this implies x squared plus y squared plus z squared minus 3 equals 0, i.e. X squared plus y squared plus z squared equals 3. And again, we're working with integers, and so therefore x, y, and z are equal to 1 or minus 1 respectively. And so again, we can test the values, and that's not very hard just by looking at the initial equations to see which work, and we'll get the same solution. Okay, but this to me is much easier. And also what this tells you from this line here is that if x, y, and z were allowed to be anything, then you would have x squared plus y squared plus z squared equals 3, which is the equation of a sphere, right? So if you were working over the whole real numbers rather than just the integers, then that's why I said you would have a sphere of solutions, I think. Okay, I don't think there was any more I wanted to say about that, but yeah, you will improve with these with practice, and it's about noticing the symmetry. So I hope that was useful.